Welcome back. In today's lecture, you're going to learn about some key ingredients for inferential statistics. Researchers use inferential statistics to make general conclusions about a population of people by using a smaller set of people, which is a sample. In this lecture and the next one, I'll introduce 4 topics that are considered key ingredients for learning about the more complicated inferential statistics that you'll learn later on in this course. Before proceeding, I want to review very briefly what I've covered in previous lectures, which are several types of descriptive statistics. Remember that descriptive statistics are used to summarize and describe a group of numbers from a research study. More specifically, we've learned about frequency tables and graphs. One specific graph we've learned about is a histogram. Frequency tables and graphs show you how many people have particular values on a variable and also indicate the shape of a frequency distribution. We've also learned about statistics for describing the central tendency of a distribution of scores, specifically the mean, the median, and the mode. And finally, we've learned about measures of variability, such as variance, standard deviation, and range. These measures describe the amount of spread or variation among scores. In particular, the standard deviation is most commonly used and gives us a sense of how much scores differ from the mean on average. Together, the mean and the standard deviation are the 2 most commonly used and important descriptive statistics that are used in psychological research. The mean and the standard deviation are also the basis for the inferential statistics and the key ingredients for the inferential statistics that we'll learn in this lecture. So here are the 4 key ingredients that I will review in this lecture and the next. This is the order that they're presented in the textbook chapter. So in this lecture, I'm going to review what's in bold, which are z-scores, and then I'll also return to the distinction between samples and populations, which I touched on in the very first lecture. So in previous lectures, we've learned how to describe a group of scores in terms of the mean, as well as variation around the mean. Today, we'll learn how to describe a particular score in terms of where it is located in a group of scores, or we could also say in terms of where it is located in the frequency distribution. Specifically, we're going to use the mean and the standard deviation to create something called a z-score. A z-score describes a score in terms of how much it is either above or below the mean. More specifically, a z-score is the number of standard deviations that the actual score is either above or below the mean. Let's do an example. Consider this survey item. I can learn statistics with a response scale from strongly disagree to strongly agree. We have a particular student who answers 6. They agree, I can learn statistics. What can we say about this student? Well, we can say that they agree with the statement because their score was 6, which corresponds to agree. And I guess based on the response scale, we can say that they have some degree of confidence. But only knowing this student's score, we can't necessarily say anything about how this student might compare to other students that are also asked to answer or give their rating to the same statement. So, if this item reflects confidence in one's ability to learn, we don't necessarily know whether this student is more or less confident than others in a class without additional information. Okay, well, what if we know the mean and the standard deviation from a sample of 59 students that were given the same statement and asked to make their own rating. Well, with the mean and the standard deviation, we can see that this student scores a little bit below the mean. The mean is 6.2. So we can say that their score is lower than average. Going further, we can express this person's score as a z-score. You can see here I've presented the formula for calculating a z-score. What we do is we subtract the mean from the score to get a deviation score. You'll see that in the top of the formula in the numerator. Then we divide the deviation score by the standard deviation. So here we have the calculation. So for this particular student with a score of 6, we'll take 6 minus 6.2, 6.2 being the mean, and then we'll divide by the standard deviation, which is 0.8. In the numerator, you can see that this student had a deviation score of negative 0.2, and when we divide the deviation score by the standard deviation, we get a z-score of negative 0.25. So this person's z-score is negative 0.25. What this tells us is that the student scored 0.25, in other words, 1/4 of a standard deviation below the mean. Note that the negative sign indicates that this student scored below the mean. This is useful information because the score of 6 doesn't really indicate how the score relates to the whole distribution of scores. If we know the mean, we can compare the score to the mean, and that will tell us whether the score is above or below average. So knowing that the mean is 6.2, that would tell us that the score of 6 is below average. But again, we can go one step further, and if we also know the standard deviation, we can indicate just how much above or below average a score is in relation to the spread of the scores in the distribution. So that's what a z-score tells us. For a particular score, it tells us just how much above or below the mean a score is in standard deviation units. Here's a good interpretation guide and a way to think about interpreting z-scores. A score of 0 indicates that the score doesn't deviate from the mean at all. Anytime a score has a z-score of 0, we know that that score is exactly at the mean, so it's average. A z-score of 0 or around 0, close to 0, means that the score is average or right about at average. A z-score of positive 1 indicates that the score is above average by an average amount. Remember that standard deviation captures the average deviation from the mean. So if a z-score is 1, that means that the score deviates from the mean by that average amount. Similar interpretation with a z-score of negative 1. Only the negative sign indicates that the score is below average by an average amount. If we've got a score with a z-score of either positive 2 or negative 2, we can interpret that as either being above or below the mean by 2 times the average amount. So differing from average by even more, twice the average amount. Now keep in mind here, what we're seeing here is a continuum. The continuum is centered around 0 and then goes to the left and to the right, basically to infinity, an unbroken continuum of numbers. So it's possible to have a z-score that is any number, and we kind of use these guidelines as a way to interpret what that z-score means. So the closer to 0, the more average that score is, or the closer to average, and the further away from 0 in either direction, the more that score differs from 0. So a z-score of positive zero point 0.5 means 1/2 of a standard deviation above the mean. A z-score of -3 means a score that is 3 standard deviations below the mean. In the case of a z-score of zero point 0.5, well, that's not really differing from average all that much. But in the case of a z-score of -3, that's deviating from average by quite a bit. So this is a useful guide to interpreting z-scores, both the sign, positive and negative, as well as the size of that z-score will tell you just how far above or below average a particular score is. So in this case, in our example, we had calculated a z-score of -0.25. We can just interpret that as meaning that this person's score on the I like statistics rating means that their confidence that they can learn statistics is just a little bit below average. Okay, some important terminology. A raw score is a score in the original metric, whatever that metric is. It could be inches, it could be pounds, it could be the extent of agreement on a 7-point rating scale, it could be IQ points, etc. Another name for a raw score is unstandardized. A z-score is a standardized score because it has been converted to a standard metric, the metric being standard deviation units. We can think of the relationship between z-scores and raw scores as something like a ruler with inches lined up on one side and centimeters on the other. In the cases of inches and centimeters, they're both just measuring the same thing, which is length. They're two different scales or two different metrics for doing so. But you can go back and forth between the two. We can convert inches to centimeters and convert centimeters to inches. They ultimately capture the same thing, which is the length of an object. In our previous example, the extent of agreement with I can learn statistics is really something that measures confidence in learning statistics. We can think of a raw score of 6 and a z-score of -0.25 as ultimately measuring the same thing, confidence in learning statistics. The raw score and the z-score are just two different ways to express the same thing, very similar to centimeters and inches. Now, one advantage of converting a raw score into a z-score is that once converted to a z-score, the same interpretation can be applied regardless of what the original scale or metric was. So that is, once scores are converted into a z-score, we don't really need to know anything about the original measurement scale because the standard rules of interpretation that I showed you on the previous slide apply. That is, if a z-score is close to 0, the score is close to average or about average, and then the larger the z-score, the more it differs from average in either the positive or the negative direction. In this regard, z-scores are very useful to be able to compare scores from two different measurement instruments. So here's an example. We've got a clinical patient, and they've got a score of 20 on a clinical depression inventory and a score of 40 on a clinical anxiety inventory. The 20 and the 40 are both their raw, unstandardized scores based on however those inventories are scored. Now, the question would be, compared to other patients, is this patient more depressed or are they more anxious? Well, this question is impossible to answer without additional information. At first, it might be very tempting to say that the person is more anxious because 40 is greater than 20, so that they should be more anxious than depressed. But that would possibly be an incorrect judgment. The reason is we don't really know how these inventories are scored. So we don't know what a high versus a low score is without any additional information. However, if we have both the mean and the standard deviation of these inventories, because we've collected data from similar individuals, we're able to compare this person's score to what is average. And if we have both the mean and the standard deviation, we can go through our technique of calculating a z-score for the person on each of the instruments, and that will then tell us how many standard deviations this person scores either above or below the mean on each inventory. In that way, we can directly compare this person's z-scores. Okay, so let's just say we know that the clinical depression inventory has a mean of 10 and a standard deviation of 5 from all patients that have taken this depression inventory. And the clinical anxiety inventory has a mean of 43 and a standard deviation of 6 based on all patients that have taken this inventory. Well, right there, we can just use the mean and we can compare 20 to 10 and compare 40 to 43. And we can already see that this person scores higher than the average on depression, but slightly lower than the average on anxiety. But we're going to go one step forward and we're going to express that more precisely as z-scores. So here's our calculation. What you see in the left-hand column is just plugging in the numbers to the formula. So for depression, the depression score was 20. 20 minus the mean of 10 gives a deviation of positive 10 or 10. Dividing by the standard deviation of 5 then gives a z-score of exactly 2 for depression. Below, we see that the anxiety z-score was negative 0.5. That negative sign should make sense because 40 is below the mean of 43. Anytime a score is below the mean, the z-score will have a negative sign. We'll use our z-score continuum to have an interpretation. So what we can see here is that the depression score of 20 actually shows that this person deviates or scores above average by 2 times the average amount on depression. Alternatively, when converted to a z-score, the anxiety score is 1/2 of a standard deviation below average. So in comparison, this person is much more depressed than average, and they're actually less anxious than average. So to answer the question, we would say that relatively speaking, this person is much more depressed than they are anxious. And that would be important because then that counselor or therapist would know to treat that person for depression instead of anxiety. It's also possible to convert a z-score back to the original metric. Here's the formula for doing so. This is really just the z-score formula that's been rearranged using algebra. Here's a little practice. Let's take that person's z-score of 2 on the depression inventory, and let's just say that we know that they scored a z-score of 2, and we want to work backwards to get their raw score. Plugging in the mean of 10 and the standard deviation of 5, we can get to a raw score of 20. Similarly, if we know that the mean on the anxiety inventory is 43, the standard deviation is 6, that person having a z-score of -5, we can work a -0.5, we can work backwards to the raw score of 40, or the original score of 40. So this might be a good opportunity to do some practice with some of these formulas and do some calculations. So let's just take the following set of scores. We've got a 2, 4, 5, or 7. I've gone ahead and calculated the mean and the standard deviation for these 4 scores, the mean being 4.5 and the standard deviation of 0.8. Use this information to determine the z-score of a person with a raw score of 5, as well as a raw score of 2, and then work backwards and figure out what is the raw score of a person that has a z-score of +1, and then a raw score that is associated with a z-score of -2. Go ahead, pause the video, work through those calculations, and I'll show you answers in just a bit. Okay, I just wanted to show the calculation for the mean as well as the standard deviation. It wasn't necessary to calculate the mean and the standard deviation since those were given in the problem, but just as a refresher to be able to say, hey, where did the mean and the standard deviation come from? So I show you, we calculate the mean by taking the sum of the x-scores, which is 18, dividing by 4 to get 4.5. In order to calculate the standard deviation, we take the deviations from the mean, we square those deviations in the rightmost column, we take the sum of the squared deviations, or SS, which is 13, sum of the squared deviations, we divide 13 by 4 to get 3.25. That's the variance, so SD squared is the variance, 3.25, and then we take the square root of 3.25 to get the standard deviation of 1.8. So you might want to just do a little bit of practice on calculating standard deviation as well. Okay, so here's the answers for calculating the z-scores. So a score of 5 is associated with a z-score of 0.28, and a raw score of 2 is associated with a z-score of -1.39. Using the raw score formula, a z-score of +1 is equivalent to a raw score of 6.3. Just looking at the formula closely should make some amount of sense if we see that one standard deviation is 1.8. So in the raw metric, or in the original metric, one standard deviation is equal to 1.8 original units. So a z-score of +1 means deviating from the mean in the positive direction by one standard deviation. One standard deviation is 1.8 original units, so 1.8 original units more than 4.5 is 6.3. Similar to a z-score of -2, we're just going to go, basically you can think about going below the mean by 2 times 1.8. 1.8 being a standard deviation, we need to go 2 standard deviations. 2 standard deviations is then 3.6 in the original metric, and we're going to have a negative sign because we're going below the mean by 3.6 raw units, which is equivalent to 2 standard deviations below the mean. Okay. So kind of the last things I want to say about z-scores is that there's 3 properties which are always true. The first is that the mean of any distribution of z-scores is always 0. This is because when you change each raw score to a z-score, you take the raw score minus the mean. So the mean is subtracted out of all of the raw scores, making the overall mean come out to 0. In other words, or another way to say this, is that in any distribution, the sum of the positive z-scores must always equal the sum of the negative z-scores. Thus, when you add them all up, you get 0. This just reflects the mean being the balancing point for any distribution. The second property is that the standard deviation of any distribution of z-scores is always 1. This is because when you change each raw score to a z-score, you divide the score by 1 standard deviation. Therefore, an average deviation is 1. Okay, finally, it's important to know that the shape of a distribution is not changed when raw scores are converted to z-scores. So, for example, if a distribution of raw scores is positively skewed, the distribution of z-scores will also be positively skewed. If the original distribution of scores is negatively skewed, that same distribution of z-scores will also be negatively skewed. Just to show you these 3 properties, I've just made up some data to show these 3 properties. So what we see here are a set of raw scores. I've calculated that the mean is 4 and the standard deviation is 1.483. I've then converted each of those scores to a z-score using the z-score formula, x minus the mean over the standard deviation. If you want to verify for yourself that these z-scores are correct, you can just plug in any one of the x scores into the formula, and you should get the numbers that I've calculated. Notice that for our raw scores of 4, the raw score of 4 is exactly at the mean, so I hope it makes sense why those z-scores are 0. What you can do is then you can take this entire set of z-scores, add them up, and divide by the number, and you should get a mean of 0. And then if you're to take each of these scores, calculate the deviation, square the deviation, sum the square deviations, and divide by the number, you'll get a standard deviation of 1. So you can check the math there if you want. And then just to show the property, I've got the raw scores on top, and I've got the z-scores on the bottom, and you can see that the shape remains the same. This was a negatively skewed distribution, and it remains a negatively skewed distribution even when the raw scores are converted to z-scores. So this demonstrates those 3 properties. Okay, so let's talk about this next topic, which is a review of the distinction between populations and samples. A population is the entire set of things of interest. So this could be all people, all women, all eligible U.S. voters, all Miramar students who have taken Psychology 258, etc. Populations are typically large, but by definition, a population is the entire set of people or things of interest that the researcher wants to make conclusions about. So although populations are often large, they could be small. So for example, if the entire set of things that I wanted to make a conclusion about was a single section of Psychology 258, I could treat that section as a population. In contrast, a sample is the part of the population we collect data from, and therefore use that sample to make general conclusions about a population. So that same section of Psychology 258 could be a sample if I wanted to use that section to make generalizations or inferences about all students taking Psychology 258 in the college. Here's another example. Let's just say that there's an opinion survey, and there's 1,000 people that are selected from a voting age population of a particular country, and they're asked who do they plan to vote for. The opinions of these 1,000 people are the sample. The opinions of the larger voting public in that country are the population. So the purpose of the research is not to find out how these particular 1,000 voters plan to vote. Rather, the purpose is to learn about the opinions of all voters in the country using this smaller sample. Similarly, in psychological research, experiments are almost always done on much smaller samples of people. The purpose of the experiment is not to find out how those specific participants respond, but rather to learn something about human beings in general under the types of conditions that are replicated in the experiment. Usually, the ideal method of picking out a sample to study is random selection. Random selection is a method for selecting a sample that uses truly random procedures. What this usually means is that each person in the population has an equal chance of being selected. One procedure, for example, is for the researcher to begin with a complete listing of all the people in the population and then select a group using some random method like a random number generator or a table of random values. In contrast, haphazard selection is just taking who's ever available, or maybe who's first on the list. When using haphazard selection, it can be very easy to accidentally pick a group of people who are very different than the population as a whole. Unfortunately, it's often very impractical, or sometimes it's impossible to truly have a random sample. Much of the time, studies in psychology, as well as other behavioral sciences and social sciences, but certainly in psychology, they're conducted with who's ever willing and available to be a research participant. So at best, a researcher tries to collect a sample that is not systematically unrepresentative of the population in any known way. These are very important issues, and there are more issues that are covered in a research methods class, but I certainly want to introduce them here on the topic of populations and samples. Okay, to wrap up, I want to review some important terminology that has to do with numbers that come from populations versus samples. Numbers that come from populations are called parameters. So the actual values of the mean or the standard deviation in a population would be that population's parameters. Usually, population parameters are not known. They therefore need to be estimated based on information from samples. Sample statistics are when descriptive statistics such as the mean and standard deviation are determined from scores in a sample and are used to estimate or represent population parameters. Population parameters are usually symbolized as Greek letters. So we can see that in the center column. The symbol for the mean of the population kind of looks like a U with kind of a straight line in front of it, kind of like a squiggly U. This is the Greek letter mu. So I've included a pronunciation guide. It kind of sounds like a combination between a cow and a cat, mu, or what a cow and a cat, the sound that a cow and a cat would make, mu. All right. The symbol for population standard deviation is the lowercase Greek letter sigma, and then the symbol for the population variance is sigma squared. In the rightmost column, sample statistics are symbolized using Roman letters, the italicized M for mean, and SD and SD squared for standard deviation and variance. It's very, very important to remember these symbols and to keep these symbols straight because they represent similar things, but like a mean, but means that are very importantly different. So while mu and m both refer to a mean, one refers to the mean in the population and one refers to the mean in the sample. And it's very important to keep those separate. In fact, we're going to use formulas in subsequent lectures that include both a population parameter and a sample statistic, so it's very important to differentiate those. It's also important to remember the names. So in subsequent lectures, I'll be referring to mu and sigma quite often. And it is just an easier way to refer to the mean of the population to call it mu instead of repeating the mean in the population over and over. So please commit these symbols to memory. We'll be using them throughout the course.